right, let's get started here. Thanks for coming. I know it's after lunch session. It's always hard. I hope you guys are all caffeinated because we are here to blow you guys out. We were kind of thinking of, Josh had that idea to think of having a huge fan here so they can literally blow you guys out. But instead we'll do with our slide and code base, okay? So my name is Nilanjan Raychaudhuri. I have Josh with me. Both of us kind of work for Typesafe. Josh, you want to talk about what you do for Typesafe?
Yeah, so my name is Josh Suereth. I work on the Scala language. I'm the release manager, and then I also make sure that we have builds and that native packaging and stuff works. So if you ever download anything from Typesafe, that probably has my hand in it somewhere. So feel free to send hate mail. It's joshua.suereth@typesafe.com. Anyway, I also have written a book called Scala in Depth. So.
All right, so I work on the professional side of the things. I do lots of consulting, so I go help client using Akka, Spring, and the framework. I kind of love this called Play Framework, which is kind of web framework. I'm still working on a book called Scala in Action, which will get released very soon, I hope. And never write a book. It's a really hard thing to do. Okay. So why we are here? So we're going to talk about a framework called Akka, which is completely new for if you guys are from a Spring developer background. So I'll do a quick poll to just get a little bit of understanding. How many of you heard Akka framework before? Well, that's pretty good. How many of you have done Scala programming before or played with Scala? Okay, that's awesome. The people who are... Okay.
How many people heard of Akka before today or this conference? Okay, good.
That's awesome. Okay.
So no cheating.
So people who haven't heard about Akka, don't be disappointed. We are here actually going to talk about. But what we've decided to do, instead of talking about the framework and all the cool features that framework has to offer, we kind of created a storyline here. So we're going to talk about some problems we are having, and we talk about how Akka framework kind of solves that problem. And we think that's the kind of a best way to learn new kind of tools and paradigms. Because the common question is like, oh, these are all cool features, where I can use it in real world. So we kind of try to address that question here. So our storyline is Josh and I opened a hotel business, finding cheap hotels. We do it for the conferences, technical conferences and whatnot. And we help finding people, hotels who had better Wi-Fi service. Okay, so we kind of had that business is going great because of the conferences and everybody is loving it, but we kind of having some problems with it. So the initial interaction with our application or site is people come in and they kind of search. Hey, I'm looking for this hotel. I'm going for a conference in this city. I want this hotel. So search is the main first interaction people have. And we're kind of having scalability issues with that. We are not able to handle all the load that we are getting, all the requests that we are getting. So it's kind of hampering the experience, okay? And it's making our customers really, really unhappy. Okay, that's the problem we're dealing with. Our application is built using Spring Embassy. So this is kind of the home page of this application looks like. So we're kind of a little bit lazy. So what we decided is take one of the Spring sample application called Travel. You probably have, Spring developers probably have seen this application before. And we kind of started using this. You know, we are a startup. We're kind of not investing too much on this business. So we are here now. Our business is doing great, but we have the scalability issues. Hold on. Oops. Okay. So we kind of looked around and we've decided that we need a solution that kind of provides this kind of benefits. First, it needs to work with Spring. Okay. We have an investment on Spring and we really don't want to get rid of that framework. We love Spring. Okay. And it has to be easy to implement and developer friendly. It's very, very critical. Like we said, we care about developer. We care about you get a better Wi-Fi service at the hotel. So at the same time, we care about developer experience, how easy that is to build. Because we have all the horror stories we heard about people building concurrent application, and which is very, very hard to do. So what are the usual suspects when you think about concurrency? Go ahead. Scalability. What are the usual suspects you guys go for? Threads. What else? Messaging system, JMS. So we're going to talk about this. Thread, we personally think Thread is like an assembly language of concurrency. Okay? Thread is such a lower abstraction, I don't think it's going to make our developers really happy. Because when you do threading, you have to worry about state, then you have to worry about synchronization, locking. It really, really makes happy. And all those bugs that you have to fix at late night is really nightmare. We talked about JMS as well. JMS feels like it's a messaging middleware. It's just for Java messaging system, right? And we kind of thought about that's a too heavyweight for the type of problems we are trying to solve here. Okay? So we decided to use a framework called Akka. Okay? So what is Akka? What is Akka offering us? Okay, by the way, Akka stands for a tallest mountain in Sweden, right?
Tallest mountain in Sweden. We won't tell you what it translates to, though. It's the tallest mountain in Sweden. It's a goddess of Sweden, known for intelligence and sophistication.
Okay. So we kind of decided to use Akka. Why? Because we kind of liked the idea behind this framework. The idea behind the framework is this completely event-driven framework, okay? And it allows you to build scalable and reliable application. Two of the words that we're looking for. Not only that we want our application to run and scale and handle load, we also want our application to be reliable. It should be up and running, okay, as much as possible. Reduce the downtime. And it, at the end, has to run on JVM, because we all love JVM. That's why we are here, right? And so the philosophy is very impressive for Akka, because the core idea is that you want to make it easy for developers. You really don't have to be PhD or scientist to write correct concurrent or multi-threaded or concurrent and parallel application. You can actually do that by using right set of abstractions. Okay, that's what that's what Akka provides us to here. Makes it easy, so that's a given point. Okay. So why Akka? Akka has this notion of scalability two different ways. That is, one, you can scale up. For an example, you're hosting your application in single server, so you can take the leverage, take the benefit of all the cores that are available to you, right? I mean, we all read that paper of that free lunch is over, right? Now the CPU architecture is becoming multi-core. We want to push to a paradigm which kind of allows us to leverage all these cores available at the system.
Yeah, one of the big things with scaling up too is if I have an application running on a 4-core machine and I move it to an 8-core machine, how much more performance should I see? Well, if I'm not using threads well, I probably see somewhere between like 1.5, maybe 2. But I'd like to get all of that performance. You know, I'd like to. So Akka actually has really, really good scaling up functions. Essentially, it's almost completely linear. So you get a little bit of a tail end as you scale up, but you know we're testing it on 64 core boxes is our test bed, and you get an almost linear scale as long as you design your system using actors. So we'll cover the topics later, but scaling up is the first focus of Akka. You should be able to use a single machine to the full extent of its ability.
Now, at the same time, since the cloud computing becoming like an utility these days, right? Almost everybody is trying to leverage that functionality. We also care about a solution which allows easily to scale out. If you have a cluster system, how can we take our application and make it distribute? Okay, so that kind of function. And not to mention this last point, but not least, is the fault tolerance. We want to make our application reliable. Self-healed itself. This is one of the very, very important features. We're going to have some examples for that too.
That's the marketing term, if you want to write that down. Self-healing application, okay? That all of your applications should have that on them now, and your resume will look way better. Just saying, okay.
So why Akka? We're going to continue with this term because there are some other important benefits that we care about. You use it with Java today. Okay, Akka has a Java API, so you can take the benefit of Akka in your current application, even if you're not using Spring. Okay, an option of leveraging Scala later. So Akka has two set of APIs. One is Java and one is Scala. We're going to use Scala API here. This is a gateway. It could be an easy gateway drug for you guys to start using Akka and then slowly migrating yourself Scala and take the benefit of that language has to offer.
But you don't have to use Scala.
You don't have to.
In fact, we have big clients that never ever touch Scala, and you can still make use of Akka. So again, we use it mostly so that code fits on the slides.
And it's the biggest benefit because we talk about this and we have to care about our deployment architecture too, right? I mean, we are already invested so much money on this application servers that we have. Can we take benefit of them? Yes, you can, because it's going to perfectly fit into your current deployment infrastructure because Akka is just going to be another jar file. So that's pretty amazing. So all these points kind of convinced us in our hotel business to use Akka here. So we will use Scala, and I hope you guys are all right with that. But the biggest thing about Scala is even though you haven't looked at the language before, the code will read as a pseudocode. Okay, most of this should make sense. If it doesn't, please raise your hand. We are here to explain the code. It's very important we get that code, right? Because that's what we'll understand. And the reason we are using Scala because it has a feature called pattern matching, and Josh will explain that in detail. We're going to come to that slide, how that works. And integrates with Java, so that's our kind of benefit here. So what's the problem you're solving here again? So I want to iterate back again. Say we are solving a searching the hotel problem. We want to make the search scalable as possible with all the infrastructure that we have for our Spring application. So the code base that we're going to use is already hosted in GitHub. So if you have a laptop with you, I would really encourage you to go there and download the code so you can start looking into it parallelly. So it would be awesome.
Yeah, it's a standard Spring Java app, and then we have a basically package that has all the Akka and Scala code. So you can go and you should get comfortable with what it is. It's just the basic Spring Java, and then we have Scala in there. So feel free to download and follow along.
And it uses Maven. It will be perfect example for you guys in case you guys want to use Akka in your project. So this is our current flow. The web page that we just saw there, when we are searching hotel here by clicking this thing. So our current flow is, oops, why are we getting there? Sorry, our current flow is that we have a client, in this case is a browser, and then we hit the controller, which is a Spring MVC controller, which invokes a service. There is a service called JPS service, which gets injected to the controller, and the service directly hits the database. So the first change we're going to introduce there, so because we are slowly getting familiar with actors because it's new to us, we're going to just introduce an actor there which will hit the database and cache the data for us. The first solution we're going for is that get the data loaded in memory and kind of index it. Okay, that's our first iteration, okay? So that our search improves a little bit. So this is, so before we look into the actor, let's understand what is an actor. Okay, what is we are talking about here? So actor model is, actors are very, very much object-oriented concept, okay? Most of us are object-oriented developers here, so it's going to be very easy to understand this model. So it's like an object, but it's reactive. It doesn't do anything by itself. You have to send a message to the actor to make it do something. Okay, your typical objects, your objects has an API, get, set, do something, all these methods. For actors, the only API is its mailbox. Only way to communicate with actor is by sending messages across. So when you send a message to an actor, some point actor will read that message from the mailbox and execute some action. Okay, that's the essential model. Another important thing actor allows us to do, which helps in concurrency, is that actor encourages to have no data shared architecture. So actors is an object, that means it has data and behavior, everything there, but the data is not shared with anybody. Okay, that actually makes it easy to concurrent and run parallelly. That's the distinct difference. So when you think about actor, that means anywhere we can think of using objects, you can actually use actors now. Okay? So what is an actor? So actor is a unit of code organization. That's exactly what we do with their components, right? In Spring, you have controller is an object component. Your model is an object component. In actor model also, Ian covered this in its last presentation too, where each of these components could be replaced by an actor. Okay? It's a code organization. It also keeps the policy decisions separately. So for an example, you can have a thin actor layer on top of your application, which we were trying to do here, which gives you policies of concurrency, parallelism defined in a separate layer. So your business layer could be core different, separate. You want to talk about the code layer?
Yeah, so let's take a look at what actors are. When I define an actor, I create a class that extends actor. I hope that this looks familiar. We're in a package. If you're following along in the code base, it's under travel.actors. We import Akka actor and Akka props. We don't actually use props right now, but what are props for actors? An actor needs props to act. So, you don't have a movie without props. Anyway, props are how you create actors. And then we have Akka event logging. That's we just show you the import because these are going to be standard if you're using an actor system. We have the logger there. We actually don't make use of it in any of our code to keep it simple for you guys later, okay? But there is logging. It works great. Anyway, class sample actor extends actor, and then you define a receive method. The receive method returns the behavior for the actor. Okay, this is pattern matching here. Pattern matching is receive takes in some input, and I have case statements to determine what to do based on the input. If I get the exact string test, I will say received the exact string test. Otherwise, I'll say I got an unknown message. Now, this is actually really powerful because we can do other fun things. Here is the first solution using actors to find hotels. I want you to look at that receive method right there. It says case hotel query. Hotel query is a class. The class has inside of it a search criteria. Okay, so hotel query is our message that we are sending, and in the case statement we're basically doing is instance of, but it looks like a switch. So I can have a whole bunch of case statements that do my is instance ofs, and I can actually nest these things and do all sorts of crazy stuff with pattern matching. If you want to talk about that later, we can dig into how rich pattern matching is, but you can do some really interesting case statements that we'll show you in the code. We actually encode queries of death. So if we get a query for the string timeout, we actually have different behavior than just a regular old query, and it's all in this case statement. It actually looks pretty good. So we'll show that later. Anyway, pattern matching is one of the main reasons we go to Scala. Okay, so anyone have questions on general pattern matching, what it looks like? Does this code make sense, what that receive is doing? Yeah. Where is what? Search in that case statement. Oh, search is a variable, actually. So hotel query is a class that has one member in it, which is the search criteria, and search is a variable that gets bound. So now when I type search anywhere on the right-hand side, that's whatever came in on the query. That's the actual value. I give it a full name. Yeah.
So actors are backed by it. Go ahead, sorry, ask a question.
Yes, it's specifically like Akka is kind of a library that's intended to look like Erlang.
Yeah.
So my question based on the comment is, I know by reputation that Erlang really relies on super lightweight processes, and kind of everything's organized around the fact that it's very cheap to spin up the process. If the process dies, no big deal.
So that's, yeah.
How does that compare to for Akka? Can they rely on that?
Yeah.
Josh, could you repeat the question?
I'm going to repeat the question, but you're basically giving away part of the talk. Okay, so Akka is designed around the Erlang model, which is actors should be very, very, very cheap to create. Very, very cheap. These things should be so cheap it's like creating a regular object. On our one test machine, it's 12 core, 16 gig of RAM, I think. Maybe it's only 12 gigs of RAM. We can make about 9 million actors on just one JVM. And we can send 3 million messages a second. So that's our what we consider a base level server machine. Statistics. If you go to our 64 core machine, it's a lot more. I actually don't remember the number. Yeah, you're pegging everything.
So essentially, for actors, you're constrained by how much memory you have. They're so cheap. I mean, for your this standalone machine, we can actually have the millions of them.
So if we'll cover a little bit more as time goes on, but essentially the question was how does Akka relate to Erlang, and it relates very well. This is basically Erlang for the JVM.
Yeah, I mean, my question is incomparable in terms of that performance, because you can talk about the Akka model, but if it's an expensive implementation, then
So in terms of performance, Akka is actually it's the fastest actor model on the JVM, and it's very comparable to Erlang. Yeah, we definitely are watching Erlang a lot. Yeah, there's a few differences in terms of isolation. The Erlang VM can get better isolation because they control the VM, and Akka is built on top. It's a library, so we can't actually get in and change the way the VM works. Although we kind of want to, we might. I don't know. We'll see. Anyway. Okay, so anyway, the receive method, we get our hotel query search. Here, does this work? Yeah, we get the search, And then sender is a method defined on actor that tells me whenever I call it, it gives me a reference to whoever sent the message I'm processing. Okay, so I have a return address. And this bang means send that actor a message. And that's this thing on the right-hand side. Well, I send it the result of find hotels, which returns a hotel response. In Scala, we invert types from Java. There's a reason why, but I won't get into that in this talk. Anyway, so find hotels takes in the search criteria, returns a hotel response. Here I'm just responding with the response. If you look at how this is implemented, we were really, really lazy for this example application, so it's kind of a terrible search index. You would not quite do it this way, but essentially for every search string thing and hotel in our index, if that search string contains the lowercase version of the search string passed in by the user, we're going to yield that hotel. We return it as a result. And then here we take all of those, throw them in a sequence, and return the response. Okay, this is working Scala code. It's actually that simple to search through collections and multiple ones. This is called a for expression. Okay, for expressions in Scala look like SQL. Okay, from index where S contains this yield or select hotel. That's essentially it's kind of like SQL, but you work against collections. So index happens to be a map of string key pairs, and anyway, don't want to get into the details, but that's what hotel response is doing. Again, the reason why we chose Scala is we can actually show you the entire implementation of searching in one slide. Yay. Okay. We need to initialize the Akka actor inside of Spring. This is where all the fun comes in. We get an annotation that says it's a service on our Akka search bean. We're going to extend our search service pure Java interface. Okay. We're going to say that this thing is a singleton because there should really only be one actor system. Actor systems take up a lot of CPU. We don't, we want one, and then we're going to use Akka to scale this thing out on a single machine. We pull in our persistence context so we can load in the hotels when this thing starts. We instantiate an actor system. By the way, in Scala, your constructor is the body of the class. So as we fall down, this is construction happening. Okay? So the first thing we do is create the actor system. We have a post construct where after Spring has embedded the entity manager, we define a method that figures out how to query for hotels. Entity manager, create query, select H from hotel. And then for every hotel, we detach it from Hibernate. Okay? The nice thing about our sample app from Spring is there's no way to add a new hotel. In real life, this whole system has to have a way to inject hotels. That's actually a more advanced talk that we're not giving now. Okay? But that's, if you can talk to me afterwards if you're interested in how that works. Okay. But we have to detach the Hibernate objects from the sessions so we don't like blow up, the Hibernate second level cache. This is a cache that we are storing on our own. And then we return those hotels. That's what get hotels does. And we create a props for the actor. The props is how it's created. This is a function that basically says if the actor dies, here's how you recreate it. We call new single actor search with this method that will go query the entity manager for hotels. And then we call, in the system, we instantiate the actor and we give it a name, which is similar to your IDs in your Spring config. These names are how you look up actors and find things. So what we've done here is we created a component in Spring that represents the entire actor system, and we're embedding our scale up, cache in it. And it's a really, really nice way to start integrating Spring in with Akka and Akka with Spring. Because you can keep your application, you can pick the piece that you want to move to Akka, and you can throw a whole bunch of actor models underneath and expose everything with interfaces as components to Spring and get this asynchronous behavior, this scaling, that sort of thing. Okay. So then now we have to show how to use it. Okay. This is later on in that same class. We define a method that takes the system and grabs the current actor. We only have to do this once, really, but I define it as a method because I am lazy. I just wanted a method that worked. Anyway, I didn't want to have to do it in the post init and have a var that called me lazy. Okay, override find hotels. This is our pure Java interface method that we're overriding here. We return the Java util list. What we do is we define a timeout on the actor system of how long we're going to wait for a response before we give an error back to the user. That's 5 seconds. Question mark means we're going to send in a hotel query and we expect a response. Okay? So we send in our hotel query. We expect a response of type hotel response. This is going to come back at some point. The type of this, notice I didn't write a type, Scala infers it, is a future response. If you're familiar with the Java util future, this is akin to those, but slightly different. Here we use the await to say, await for that future, for infinity, actually, because we have a timeout of 5 seconds guaranteed to blow up here. And then we return it as Java. Yes?
There's a difference between giving the actor a message with the question mark or the exclamation point. I know it's not up there.
So this is the tell versus ask principle. Okay, so this is actually in Akka. This question marks are a sign that you cannot scale at this point. This is the part where you stop scaling well. Okay, so question mark is asking. It's a two-way communication. I'm sending a message and I expect a response. Telling is the exclamation. Exclamation, I send the message, don't expect anything to come back, and I don't care. So again, with actors, if you tell all the time, you actually end up with a much better communication structure. The two-way synchronous actually it usually creates huge bottlenecks in your system. Those are usually points that you either want to find a way to use tells and send ACK messages and control what happens if things drop. Here, we're using this timeout of 5 seconds. That's a very unideal way to handle failure. Anyway, yeah, but that's the difference. One sends the message, one sends and expects a reception.
That's still non-blocking though, because you get a future back. That call will immediately return. That's why we're calling away.
This is the bad part here.
Yeah.
Yeah. Okay. All right.
Yeah. So one thing that so I mentioned, I just want to mention one thing in the slide. Is one thing I mentioned, the actor is abstraction of a thread. So where this threads coming in? Where are threads? So what actually happens is that when you send a message to an actor, and we saw the picture that actor has a mailbox and the message queues up there. So this actor system essentially is an abstraction over a thread pool. There is a thread pool running somewhere, which is managed by Akka itself. And one of the thread from the pool gets assigned, which picks up the message and execute your receive block. Okay, that's what happens behind the scene.
The beauty there is that one thread pool of, say, 12 threads can support hundreds of actors.
Right.
And I didn't mention this, we should actually go back. Yeah. If you look at the actor, there's absolutely no locking whatsoever, because we can only handle one message at a time on a given actor. So how do you scale? You fragment out your design such that every actor is very small, very well defined, and there are a whole ton of them. Okay, and that's how you get actual scalability. But the beauty is I have state, and I don't have to do any form of locking. So we'll show you as we go, this actor is not going to scale well, and we're going to make it scale well as time goes on. We're going to show you how to fragment.
Which is a very interesting guarantee to have. So that means in a parallel computing world, you can have a mutable state. Not that I'm telling you to have a mutable state, but your actor could have mutable state. But the actor system is going to guarantee you by at a given point of time only one thread is executing your code, which is a pretty interesting guarantee to have. So I understand actors, and the question becomes is how this actors kind of fit in. How do I design my application using actors? So actors kind of follow the similar topology like Spring have, okay? Actors are encouraged to have like a hierarchical model. Like think of it, your organization. You get a work, your manager doesn't do anything, he delegates all the work to you, right? and you have this whole organizational structure, and actors kind of model that very well. So when you start an actor system, it starts with an actor. We call it the guardian system actor. This is kind of the parent of all the actors you create in your system. And then Josh was showing you this code that we call system.actor_of. In this case, we are creating a new actor. That actor immediately becomes a child of that parent. So there is a relationship going on, implicit relationship. Okay. Now this actor can again continue to spawn a different set of actors, and that's actually it's very much encouraged in Akka, because what interesting model that actor system allows you to do is divide and conquer. You get a work, you break it into tasks and give it to your child. spawn it out. Because creating actor is so cheap, that's a very good pattern to do that in Akka module.
Very importantly, you can dynamically do that. So you can have an actor who's churning through work, and you can have somebody who's watching him and says, hey, you're taking too long. We're going to now split you into 12, maybe,
Right.
we determine is the right size. So you can dynamically adapt this topology at runtime.
Very good. Yes. Since the topo, any question on this? Yes.
So, the question is there support for a state machine based view of an actor? Since you can have actors that move from state A to state B based on messages they receive. Yes, there's an actually really awesome, it's called the FSM API, finite state machine. It's actually really, really nice in Scala. I use it when I use Akka, half of my actors are FSM and half of them are regular. So we don't cover that here, it's a bit too much, but definitely look that up. There's a Scala library. I believe there's a Java equivalent, but I don't know.
Yeah.
I don't think it's quite as nice. Yeah. Sorry.
Yeah, go ahead. No, it doesn't have to be. It's just a graph. It's just a hierarchy. So one way to think about this is that your hierarchy kind of resembles your economic organization, the way you structure your organization. Ends up very similar to how actors are also architect your application, how the architecture evolves too.
It only looks like a binary tree to fit on the slide. So, yeah.
So since it's in hierarchy, so it kind of implies with the next thing we're going to talk about. So you created an actor, right? You have an actor system with all the actors running on the system. How can you look up an actor and kind of send a message to the actor? Joshua was talking about it a little bit, right? Looking up an actor. Since it's from hierarchy, the lookup actually works like a file system. So he was doing system / thing. So all the actors kind of have a name associated with it. And those names kind of from how the file system works. So that's Foo. Since Foo created the A actor, the path becomes, we call that an actor path. You need an actor path to look up an actor. So it's almost like a JNDI lookup, but for actor system. Okay? That's kind of an interesting implication. So what we have seen so far, we have seen is that what we have done, we took an existing Spring application, we kind of took a part of it, enabled as a cache in memory using an actor model, which is kind of a completely different than the way the Spring kind of work, right? But it kind of nicely fits in because you can write it in Java or Scala and it runs on JVM. That allows it. At the same time, actors are like unit of computation, right? You can take a computation, a method or whatever, and kind of transform that to an actor, right? It allows you to do that. Another important thing we learned is that actors are stateful. We always worry about state when you do concurrent programming. Oh my goodness, how should I do synchronization? How do I do locking? But actors provides that guarantee that you can have a state in there, but the state is safe as long as you're not sharing with anybody. Because the actor system will guarantee that at a given point of time, only one thread is executing your code. And remember, we started out with, we are looking for a solution which is easy for developers to implement. We just saw actors are nothing like an object. We don't have to worry about any low-level stuff like threads. So it's a very nice abstraction about that.
Any questions before we go to the next section? Okay.
All right. So our caching system is working nice. Then we realize, wait a minute, we have one instance of actor running, right? So that would essentially means we have still a single threading problem. That means one thread could execute that code. It's not parallel yet. We have all these cores that's sitting idle there. We are kind of not using it. So we kind of decided, what if we take that single instance and make it multiple instances running at the same time? So instead of one instance of actor running, multiple instances of actor running, you can do that. That pattern is called router. When you have multiple instances of an actor running, you can place a router actor in the front and use some sort of routing policy. It could be round robin. It could be based on the smallest mailbox size. It can detect that who has less number of messages to process and send the message there. And this router could actually forward the message to actor. Okay? Now this is the first time we took our application by, Josh will show you the code changes. By making few little code changes, we just made our application parallel. Show the code.
Yeah. Oh, so one important thing here, by the way, is the fact that actors aren't parallel. It's not like I'm taking something and farming it out parallel. They're about concurrency, doing multiple things at the same time. Okay? So how do I skip the animation? Come on,
Almost
animation. Almost, sorry, guys. Okay, here we go. So if you remember, this is the exact same code as before. The only thing is the highlights. So here, after we create our props for how to instantiate the actor, that was the function that creates the actor, we create a round-robin router for 5 instances. And then we call search props with router and pass in the router when we construct the actor. That's it. Now, instead of creating 1 instance of the single search actor, we have 5. And there's a router in front of them that passes messages. This is a pattern that you could code yourself if you really wanted to, but Akka just provides these routers by default. Yes?
So when you're creating your search box, is that treated as like a prototype for construction of the actual actors?
Yeah, so the question is, when you create search props, is that a prototype for constructing an actor? And the answer is yes. Props are, if an actor fails, we need a default way to know how to restart that portion of the system, and so props is our mechanism. If an actor fails, we're going to try to recall that function to regenerate that portion.
You're sharing the same attached object list for all the actors. It's the same thing.
Well, so that's a good question. That's a good question. Are we sharing the same object list across all the actors in this implementation? Anyone have a guess? Yes or no? No, we are not. We're actually requerying every time, which is terrible. So we're going to fix that next. Yeah, so next we fix that. But yeah, we're passing the method that ends up requerying. If you wanted to pass the same data to each one, you would instantiate the data in memory, and instead of passing the method getHotels, I would pass the actual data object, the list itself.
Is that a Scala feature that you can pass a function?
Yes.
Yeah, so
Because your constructor defined the data type, it didn't say that it was a function.
yeah, so the question is this a Scala feature that this is a function? And the answer is yes. Scala has the ability. Props says I take basically a 0 argument function that returns an actor. Okay, and Scala can take any expression inside of that constructor and turn it into a function for you without you having to lift a finger. So again, it's very nice. In Java, you would actually instantiate an anonymous like actor creator object and then pass that to actor of, and that's how that would work. You'd have to create the anonymous class. Scala will just make you the closure. Yeah. Okay. Cool. So let's say. Oh,
Good.
yeah. So we're running and we're having issues right now with our actor system, and we need to scale out across our Akka cluster. So we have a set of Spring applications running, and we've gotten Akka to communicate between them. What's really nice is we can create a configuration without code changes and change the provider for actors to this remote actor ref provider, and we can change the search service front end link to say you communicate here. So for the search actor, we define a remote path, we define a protocol, we define which actor system to find that guy on, and we define what the host name is. So without changing the code, I can ensure that my actor system actually lives over on this box here. And I can take portions of my application based on that path and move them around in my cluster.
So we have taken the location transparency idea very seriously. I mean, till what reasonable extent we can take that idea. So when you're building your application, you can still work with local actors. But the concept of scaling out, taking your actor system running on a separate machine altogether is just a deployment concern. It's a configuration change.
And so if you look at the topology of your system, that big tree, and you determine this subtree here, I need to move it out into the cloud, it's a configuration change. I take that path and I say this needs to go over here, and I can move all those actors onto that block of code. Yeah?
So can you swap out, like if you wanted to do this over SSL or other protocols that
So the question is, can you swap out different protocols? I know that there is a hook to have your own protocols. The default is the Akka protocol, which is Java serialization. And then we send that inside of like a protocol buffer for, anyway. Yes, you can have other protocols. I don't actually know the details. I apologize.
I mean, they're a very serialization mechanism, but out of the box, I don't think it supports anything else right now. But it's easy to implement. You see the provider up there? Provider is that critical component, kind of tells you how the actors will communicate. Yeah. So it implements an interface. If you can implement the interface, it will work. Yes, please.
So the question is it on a well-known port? Yes, you could put it on a well-known port. You actually can configure which port actors sit on. Yeah. You could implement like HTTP and stuff. I don't want to get into remoting too much because that's a little bit beyond the scope of this talk. We just wanted to show you that basically it's a config change and possibly a few implementation helpers like a different remote actref provider. And because of the way you've designed your actors, the core of your logic is this actor system, right? Figuring out whether or not to send a message to another cluster, you can do that as a deployment configuration. You don't have to, yes?
Can you have multiple remotes?
So the question is, can you have multiple remotes? Yes. You mean for the same actor?
Yeah. So I have the same actor on different machines. They all perform the same function, all have the right resources available. Can I just configure it to say, just pick one of these machines and send off my message?
So the question is, can I have multiple machines, multiple of the same actor on different machines? So in the deployment configuration, you would give each of them a different name, and you would put a router in front of them that would configure just send off to one of those. There are a bunch of different router implementations. You can look for like smallest message queue. Akka 2.1 is coming out with even more cluster support and remote support. So that it's RC1 as of silently yesterday. I think they announced it today. That's going to have more. Akka 2.2 is where automated moving around kind of comes, but we're working towards that. So with Akka 2.1, you should be able to say like this Akka is on the cluster, and cluster membership is really easy to push things around versus remoting. Remoting would be, this machine is specifically over here. Okay, that's what Akka 2.0 has. Akka 2.1 has on the cluster. I can, just address something somewhere else on the cluster easily. I hope, yeah. So the question is, where does the configuration live? I don't know if you've seen the Typesafe config library. The Typesafe config library allows you to have a whole bunch of different locations, and you can actually change where you look in your code when you have your startup. So I believe by default it's the class path, and you can add like file URLs, you can add HTTP locations. You can add a whole bunch of different places to look up config, and that's all from the, this is just using the Typesafe config library. So if you look at that and its available options.
So, we're going to get that in clustering support. Right now it's not there technically.
Yeah, and so that's, the question was, there's nowhere that I can do this at runtime, change this config. And yeah, the answer is when we get clustering support, you'll see that. The other thing that I want to show you throughout the rest of the talk is adaptively inside of code, altering topology and altering your layout is a very important piece of actors. So hopefully you'll see how powerful it is now, and when the full clustering support's out, it'll be really amazing. So. Sorry. We were missing that for someone who asked about port. Yeah. Okay. So the
recap of this is now we have our application running, which is parallel. Not only we are leveraging all the cores we have in our system, now we have scaled out as well. We kind of deployed or make that application distributed running on multiple machines by making those configuration changes, right? So the remoting is done very transparently. So remoting is essentially theoretically, so you necessarily don't have to make any code changes. We just simple configuration changes, you can take that. But location transparency, you have to take it with a little bit of grain of salt, right? When you do location transparency, that means your messages are now getting serialized when it's passed to the remote system, right? So you have to start worrying about latency. All this stuff you still need to consider. But at the code perspective, it's very much transparent. You really don't have to do anything special for remoting. It's kind of built in.
One of the lies of messaging that some people might try to tell you is that once you have location transparency, you can move something anywhere and it doesn't matter. That's not true because you still have to worry about your throughput and how many messages you're putting through that pipe. Right. So when you work on an actor system, it's really easy to take a component, move it somewhere else, but you want to look at the granularity of messaging between two pieces and put like pieces together. So
clustering support, we are kind of very much excited about it because now potentially in clustering support, if you're one of the node crashes, it can take the actor system running on that node and push it and recreate that node, separate brand new node altogether while the application is running. So we are very excited about that feature, which is coming soon. So one of the things that we can further talking about, like we said, we are getting popular. We are all learning about actors together, right? We are slowly moving into patterns. The next pattern we're going to focus about is that we are getting this search request. Is there a way we can kind of take that, split it into multiple smaller pieces and kind of farm that out and kind of then accumulate the result back? This common pattern is called scatter and gather. So it's one of the very common enterprise integration pattern as well, scatter and gather. We're going to try to see whether we can implement this, how to implement that in actor model. So we're going to have a little bit of graphics here coming. So let's talk about that phase a little bit. So assume root is kind of our actor, okay, which gets a message like this. So when the message comes out, so in our code base, we're going to have these two categories built in. But one of the beautiful thing about actors is that one of the core feature of actors is that it can adaptability, okay? It can adapt based on your requirements, adapt on the fly. It can add new behaviors to actors, okay? In this case, we kind of have this behavior built in. So when we get a request based on the category, we're going to split them out. We're going to scatter the requirement, okay? So the message is going to come in and it's going to split them out. So when that message computation happened, finally done happening, then each of this topic going to send the response back again. And we're going to gather all this, combine them together, join them together, and finally send the response back to the client.
So what's interesting here is in a tree of this size, how many concurrent requests can be happening? The number of nodes. Okay? If I need to handle more requests, I add levels to the tree, and basically, as after the root passes off one message, he starts looking at the next one, and so on. So I gain scalability by moving things out. So if one topic becomes hot, I keep getting searches in that topic, I turn it into a category, and I split. And all of a sudden, I have more parallelism, and it's adaptive. Okay, so let's look at how we implement this, okay? We want to implement scatter-gather. So we still have our getHotels method when we make our search actor. And what we change is we're going to create a country category actor. The country category is the root, and he splits out based on what country the hotel is in. He has a different actor for every country that we have hotels. Okay? And we'll show you that code in a second. But we pass the hotels in him, and he spawns his tree. And then we instantiate our service by creating this category actor hotel. Category actor hotels looks like this. I get in some hotels in my constructor, and the first thing I do is I have to construct my children, my topic nodes, if you will. Okay? So what I do is I group all the hotels by my category, all right, which is a function that takes a hotel and returns a string of which country it's in. And I get back the category and a list of hotels for that country. I create a new child with all those hotels, and then I create the new props, and then I yield a new actor, which is that child, right? We have this scrub actor name. This is an artifact of, I want to have country codes as my actor names. So when I look inside of like the Typesafe Console, I see search index, UK, and I can look at that particular actor and see how overwhelmed he is. But there's the names that you use can't just have spaces or dots and things, so we're just getting rid of those and making them dashes with text. That's all this does. Okay, so anyone have a question about this for expression here? We're looping over all of the grouped hotels. This is classic Scala collections here, the group by operation. So for every country and the set of hotels in that country, we're creating a child search actor. Okay? So there are protected methods here that are unimplemented of figuring out what the category is and what the child is. This is our abstract category actor. So for any category, we can have any number of children, and they're split in some random way. When we get a query, what we do is we remember who the sender was, okay, and we create a gatherer actor. Then for all of our children, we go give them the query and say respond to this gatherer actor. We haven't showed this tell method before, but when I send a message, there's an implicit who sent it. I can lie. I can put a different return address on every message. So here I'm saying, when you respond to him. Well, what does he know about? He knows who sent the initial query. So what I've done is I have an actor that looks like it's the only actor that knows about search, and I get a message from somebody. I have to remember who that somebody was. Well, this actor can't remember. He doesn't have any way to attach a session to a query. So I don't want all of the children responding to me because I don't know who to send results back to. I'm handling like 3 bajillion queries. So what I do is I construct a actor to remember that session. So that's all he does, is he lives for the state of this query, and then after he gets responses from all the children and sends back the combined results, he dies. And because actors are so cheap, this is actually really, really easy and really convenient.
So one thing to remember, sender changes per message though, okay? Every time you're processing a new message, the value of sender will be the whoever sent that message. So we are kind of keeping a reference to that so that we can remember to send a reply back.
So the category actor is the scatter, okay? The gatherer is here. I keep track of my responses in a variable, okay? In Scala, val means something can't change, var means you can change it. So every time I get a response, I add it to my responses and I check to see if I've gotten enough. If I have, I join them. When I join them, what I do, we're going to ignore flat map, but just pretend flat map basically takes a sequence of sequences and shoves them all into one big sequence of results. And it doesn't do any kind of sorting. When we show you the demo, you'll see that. You would actually make some sort of interesting join here. You would actually, in a real gatherer, okay, you would actually take all of the results and you'd order them, okay, and you'd pick the ones that are supposed to be in that search page and then return them appropriately. So this is just us being really lazy and fitting things on slides. But a gatherer essentially is supposed to take results from 2 categories and figure out how to join them and return the appropriate ones sorted. Once we respond, the gatherer, remember, he was just for that particular session. He's only for that request. He dies. He stops himself. Context stops self. I love that one. It'd be better if it was like self.die, but, you know, sounds worse. Okay, so recap. What have we done here? Well, we've increased parallelism by sharding out. I don't think we actually show this, but there is, we have the country category actor. Underneath country category, he actually instantiates city categories. So we have 2 levels, countries and cities. All city hotels live in one actor, and he has all the state for cities. And so he gets pretty good caching performance when you have to hit that city. All requests for that city go through him and take time. For any other city, if it's not going to that actor, the response is immediate. We don't have it. So we increase parallelism by kind of pushing work onto our sub-actors. That's essentially what we've done, if you look at that hierarchy. And remember, actors are cheap to create. So it's no problem if you have to create one to manage a particular request or session because they're very, very small. And again, small actors are better. If an actor is handling too much, you don't have as much concurrency in your system. Okay?
And there is another reason we're going to talk about when fault handling comes in.
Yeah.
So making it smaller kind of makes it better. So I have a small quiz for you, so we just kind of get energetic here. So who can tell me how will you know that thread crashed? So let's say you have a multi-threaded application and one of your thread kind of crashed in production. How can you tell?
Yeah, but again, which thread? Like what part of your system died when a thread died?
Well, the typical result of that is you're going to see a stack trace in a log file. That's how basically you know a thread crashed. Okay. Now we are building an application, we are building a business around that application where we tend to make money, right? And we want our application up and running. And we are all developers here, we kind of building an application. No matter how much defensive programming you do, think about all the possible things that could go wrong. Things does go wrong in production, okay? Things will crash, okay? So the question becomes is that when we kind of using an actor model, what is that mechanism that allows you to have this reliability built in, okay? Believe it or not, the model that Akka follows is called let it crash. So we've been doing this defensive programming for the last few years, so we haven't got anywhere. Then we started looking at application that builds in programming language called Erlang, where most of the stuff is inspired on. And they build application where they have 9 nines of availability, uptime, 9 nines. You know what that translates to? 31 millisecond downtime per year. Okay? It's kind of an alien technology that we don't have for JVM, right? What they're doing differently that we are not doing for our Java application. Well, the model they follow is called let it crash. What the model means is that things will go wrong, okay? Let's assume failure is a valid state in your application. Now let's talk about what we could do after that. What we could do if the things crashes, okay? But exactly. That's exactly what we're going to do. That's the default behavior we're going to do. So Akka kind of built in this model. That means that there is a fault tolerant built in. Remember the hierarchy we saw that? Your parent takes care of the child. If something happens to the child, parent takes the responsibility of recovering it.
Not only that, the parent, remember, is running potentially on a different thread. So if a thread dies and that child dies, the thread could be completely gone and toast, but the message that the thread is toast comes to the parent somewhere else. So you can actually recover a system in a concurrent environment where one thread just completely went AWOL and your system can recover.
So the supervisor model, the model that allows you to do this fault tolerance thing, a self-healing application, is built in by default. It was not there before, and the new version of Akka is completely built in. Sorry, yes? So will children know whether parents are gone away? No. But when the parent is gone away, when the parent gets recreated, all the children also will get recreated.
The parent will actually kill his children if he dies.
Yeah.
It's a very bad analogy to real life, calling it parent and child. Just saying.
Okay, so this hierarchy of this is, so whoever creates the actor, it kind of makes sense. That actor takes a responsibility, automatically becomes a supervisor. Okay, so if down there that actor didn't create anything, it doesn't care about the supervisor functionality. So what is the default behavior? What happens when things goes wrong? So there's 2 strategies. Okay, the first strategy is for one. So let's say it's part of our application. We have this parent actor and we have this 4 child here. They are all kind of linked with each other. How that link happens implicitly, right? When you're creating an actor, it automatically becomes a child. Let's say one of this actor crashes. When that actor crashes, it sends that exception, that error message back to the parent that something went wrong. I don't know what happened. When that message comes into the parent, if the strategy is 1-to-1, that parent will automatically recreate the child while your application is running. Okay, you're not restarting your application. Your application is live, up and running. Okay. The next strategy which is the default strategy, is called all for one. This kind of makes sense if you're kind of building in workflow model, like we are doing the scatter gatherer, right? So if one of the scatterer or gatherer failed, it really doesn't sometimes make sense to come up with the result. So when that happens, in this model, it will kill all the child actors and recreate them. Again, while your application is running, okay, there's nothing happening. There is no intervention. There is also manual work.
Yeah, and it escalates. If the parent doesn't know how to handle failure, what do you think happens? He fails, which means you kill all your children and go to your parent and say, hey, what should we do? This whole subsystem died. So you think about recovery topologically. When one problem with exceptions, I call a method and it blows an exception from that submodule. That submodule is completely toast for some reason. I don't know how to restart that submodule necessarily in my thread. I don't actually care. With actors, I send a error response or I time out or something, so things still happen in the other component, but the module itself knows that failure happened and can recover. So you have topological error handling.
Yes. So first of all, I want to mention that for this feature, you don't have to write a single line of code extra. Yeah. It happens out of the box. But
can we repeat the question quick?
Okay. The question is that how complicated is the strategy? How it's implemented behind the scene, right?
Not that responding, like how it gets responded, but just, I don't know, like if you say, like, I guess in the first one, if you have 3 good workers and the 4th one dies,
Yeah.
the 3 good ones have already returned results.
Right.
Then you wanted, let's say you wanted to say that and not rerun that.
Sure.
Yeah.
Sure.
So if you want to do that, the beauty of supervisors, so the question is, if I have like 3 that die and they have work finished, and then one of the workers dies, and I want to figure out how to recover and save the work that happened. Supervision is completely customizable. It's an actor. Mm-hmm. You get a message that says this child died. You get a message that says what the message that killed the child was and what exception was thrown.
Yep.
If there's an exception. So you can implement any sort of custom logic you want. These are the defaults that we put out of the box that are just useful in general to have better applications right out of the box. But if you need something specific, you can, inside of your actor, just catch these messages and deal with them. There's a supervisor implementation that you can have in every actor, and that covers how he deals with his children.
You can implement different strategy based on different types of exception. Again, the pattern matching comes into the picture.
I'm wondering what comes into the supervisor job that you catch an exception. What's coming in? What kind of supervisor?
So exceptions are coming in.
Yeah, you get specifically, you get the exception that was thrown, if there's an exception, and it's an optional exception, and you get an optional message of the message that the actor was processing when it died. Yeah. If it was processing a message, or if it just blew up, then you just get the exception. So you get it if you want, but if you don't care, really. Right. Yeah. Right. Yeah, I mean, exactly. The big thing there is you kind of want to detect message of death and prevent, keep continuing to restart. By default, these all for ones will retry for n times and then just explode upwards if you have a message of death.
So which brings a very interesting pattern too, because it's very commonly known as onion pattern, right? So if you have very sensitive data that you want to protect yourself, you should make that actor is not doing any risky job. Okay, so if you have some risky job like making some flaky connection to something which not be alive, the better to actually spawn a child actor, do the job there. Because if it crashes, you still have the data preserved in your actor. So it's a very, very common pattern. People do that. And we're not going to show that here, but when the actor gets recreated, there are standard event handlers like pre-restart, post-restart. So if you want to initialize your actor with some data back from some external data source, you could do that. It will give you the callback to do all that stuff. So, any question on this? So what's the recap here? Why we care about this kind of thing? Because we care about more about reactive kind of programming, right? We care about saying that failure, let's embrace failure. Failure is kind of valid state. Things will go wrong. Let's talk about what we will do when things will go wrong rather than defending ourselves. And errors flow up the topology, not the stack, okay? It's going to flow up the topology. So even if you don't care about it, you can delegate to your parent and the further parent and all that. So one of the actor feature, what makes an actor, so it can respond to, sorry.
So one of the reasons the Erlang actor model works really well is that the actors are completely isolated. They are separate processes, their own memory space and all of that. Does Akka give us the same guarantees about?
So yeah, the question is how, so Erlang, one of the successes is that actors are completely isolated. In their own, like in the VM, it's actually its own process, and when that dies, it doesn't affect the other actors. So how much can Akka guarantee? Well, we give you as much as is possible in the JVM. This is where I was talking about. We'd like to do more, but you still, if the JVM itself dies, you still lose your application. So that's where the clustering comes in.
Clustering will help there.
Yep. Yeah, that's just a limitation of the JVM.
And potentially, you can have a durable mailbox. You can save your messages and yes.
So
Yeah.
in Scala, presumably, you could be able to
We call that accidental shared state. Yes, I mean, the whole model pushes you not to have any sort of shared state. You can accidentally do it, but there are things in place to prevent that. Like, you can't get a direct reference to an actor from another one. You have to use what's called an actor ref, which is a completely separate object that has no notion of the internal state of the actor. So we have things in place to prevent it as much as possible, but you can still shoot your own foot off if you send a mutable list and modify it from 2 different threads. That's still bad. So when you send messages, they should be completely immutable, contain all the data that they need, that sort of thing. Yeah. Good question.
Yeah. So one of the things the actor does very well is that this is kind of when the actor created in 1973, by the way, the whole actor model came into the picture. It's pretty old. The idea was that not only it can accept and process messages, but when it's processing the message, it can decide how I'm going to process the next message. So this is where the adaptability comes in. So actors allows you to dynamically change the behavior while the application is running. So it's very, very important. So that kind of allows you to build, based on your load, you can scale up and scale down and change your topology of your application, which is very interesting. Again, one thing to, remember, recap here is triggered reactively, right? Everything happens reactively here. Actor will not do anything unless you tell it to do, send a message. And behaviors are stacked, so when you're becoming something, you still have an access to the old behavior. You can say unbecome and go back to the state. We'll talk about it, how we're going to handle. Josh will show you some code examples of this. So why do I want to do that, right? The general idea is that become sounds really exciting, like changing behavior. What is there for me? Like implement graceful degradation, like your system is overloaded. You can have your actor flip saying that I'm not going to process message for next 2 minutes. Okay, I cannot handle that. My backend system is overloaded. And again, flip it back, adding behavior saying that, okay, I'm ready to handle it right now. Okay, and adaptively transform into actor pool. You can actually essentially take an actor, and based on the load coming, you can change that actor to become a router and spawn out multiple actors. So it's a very, very powerful concept. Okay, and well, use your imagination, right? There are endless possibilities you could do with this. We're going to talk about the thing that we're going to handle now, which is kind of throttling. So we are doing a business, awful lot of stuff, and we have some external backend system. But so even though our application is scaled well, the backend systems that we are using are not scaled enough. Okay, they still are overloaded. So we kind of have to build a little bit of throttling to our system. So we still have this existing infrastructure of scatter and gather, but before that, we kind of added these 3 new actors. Okay, now the message will get intercepted by throttling actor, and this will kind of send this message to the existing system we have. Okay, now so look this interesting pattern here. So it's not waiting for this response; it's immediately ready to intercept another message. Okay, what it's doing is that it's going to dynamically create this actor called interceptor, saying I'm not going to handle the response. This guy I'm creating, again, actors creating actor is so cheap. We're going to do that. And this guy is going to handle that whatever response comes in. When the response comes in, it's going to send that to the actual caller, and we're going to have a little bit of detector. Okay, we kind of have this component to check the health of the system, how it's running. Okay, it's going to allow us to do a little bit of scaling. So what essentially happens when we have a bottleneck somewhere in our application, right? So we do the same stuff again. We have the throttler taking message, giving to our core components, but we have this Akka system always running behind the scene, right? It's kind of providing you the runtime. It detects, remember the timeout Joshua was talking about? It detects a timeout and say, hey, you did send a message to the backend system, but it didn't come up with an answer in the predefined value. So it's going to send you a timeout response, okay, a message. When you get a timeout message, the way we're going to build this interceptor is that we're going to essentially send that error message to the client as well, where I cannot handle your load right now, request. And we're going to have this detector also check in this message. Okay?
Yeah. So we're going to do a live demo, which I think I can do here. Sure. Okay. So remember I told you I hard-coded in some queries of death. So there is a query called timeout, where if I click it, it's going to wait for a minute and say, oh, looks like your search is down or your query was made of spaghetti. Let's try again. And you can see that I'm a web developer, by the way, by how beautiful that message was. Okay, so we're going to click again. We're going to click again. and it's going to continue to intercept these calls and do timeout. I think we have to do it 4 times or 5 times. Okay, so now here's what's interesting. If I put a query that should work, we're just going to search for everything with A. I think that returned because it was in the cache. Yeah, okay, that was in the cache. Sorry, we haven't showed you the cache. The cache is there. If I search for B, I get whoops, even though that's a valid query, and it should have returned because the system's overloaded. We look in our logs, you look, the fail whale just said we're okay. So the actor has now become something that accepts messages, and when I search for B again, I get a list of hotels. Where the first time I got an error saying the system's overloaded, the next time I got a list of hotels after that change state happened in the logs. So let's look at that. It's not in the slide, right? Okay. Yeah. Here we go. So the fail whale actor, okay? We have a bunch of messages we send. A query was okay. A query failed. We can tell an actor to become okay or to become bad. So the fail whale actor is the front end to the search service. I get in. I receive here a query. And every time I get a query, I can create that interceptor, and I go tell the actual service to run the query and tell the interceptor what happened. If I get become bad as a message, I become a failing actor. Context become failing. Okay? If you look here, this is passing is the block here. That's the functionality I have when I'm in passing state, and I have functionality for when I'm in failing state. Let's look at failing. Failing is when I get a hotel query, I respond with a fail whale exception. That's what I call it, the Twitter fail whale. Yay. And if I get a become okay message, then I become passing again. So I flip states. Now, what I'm using here is I'm using context become, like changing the behavior of this actor. So anytime he gets messages, that's the new handler for messages, is what's ever on the right-hand side. I could actually use context.unbecome on the failing side, because I start off as a passing actor, I become a failing actor, and then I can unbecome back to passing. Okay? But if you remember in the log, you saw fail whale becoming okay. Well, after that happens, then messages start to flow through to my search service. Let's look at the interceptor, what he does. Okay? If he gets an exception, he tells the detector that, hey, something's bad with the system. We had a bad query. And I respond to the listener for the query with the exception, and then I kill myself. I should just call that suicide, maybe. Okay. If I get an actual valid response, I respond to the listener that the response is okay, and then I tell that detector, hey, the query was okay. We had a good query. Things are going smooth. And then I kill myself. And if I get a receive timeout, remember that's an Akka-based thing, I send a fail whale exception saying the service is unavailable, because we have a 1 second SLA that we have to respond within 1 second. If we don't do it, we're going to send an error message. Okay, and I had to tell the detector that we had a failed query, it took too long, and then I kill myself. And here, in the constructor, I set a timeout of 1 second for the actor. Okay? And that's where this actor basically, if he doesn't get a message within 1 second, he gets a receive timeout message. Okay? Yes, question?
So you're telling the context to become passing, so assuming
That is changing the behavior.
Just pretend that that's a field, if you will. But
when you say lazy val passing, how does it know which?
Oh, so remember we were overriding receive here before. Lazy val is basically a value. I'm defining a function called passing, and here's the behavior, and I'm passing in that behavior, that function. We've been glossing over this.
Exactly.
Essentially, yeah.
This is changing the behavior of an actor.
Yeah. So for those who are wondering, it was about what this lazy val is. I was trying to gloss over that because I didn't want to get into too many details as long as you understand what's happening. Yeah. But this is a Scala thing. The receive blocks that we're showing you are not methods. They are actual function objects that you can swap out and in. And that's how we're doing this dynamic behavior change. In Java, you'd create an anonymous inner class. Okay. Yeah, and then we'll look at the logic for the actual interceptor service really quick. The detector, basically every time I get a good query, I drop my bad query count. If I get a bad query, I up my bad query count. If I get above 3, I swap into bad state. So that's after the 4th query, I'm in bad state. And then after I go into bad state, when I become bad, I set a timeout of 30 seconds. So I give the system 30 seconds to recover from whatever the heck it's doing now. And then I allow messages to flow back through. Okay? So I assume that 30 seconds is a good time for that system to recover its health. And you could configure that. We can do all sorts of other fun things. This is just, the examples. So, this guy. No. Sorry, man. It's a Mac.
All right, there you go.
Okay.
Any question on the demo? We kind of, there's lots of stuff happening there, but the very less code, I guess. But okay, all right. So we kind of essentially build our own throttling system where we are changing behavior dynamically while the application is running, which is interesting. Well, all that said and done, and on top of that, finally, we decided that, well, why not do some caching so that we don't have to actually do, even though scatter gather performs really well, but since we have that bottleneck on the external side, we just kind of add in caching.
Real quick there, this is the scatter gather is a cache against the database. We want a cache against queries, particular queries, because we don't want to have to hit the tree if that query is hit a lot. And since we find out that lots of people love Washington, D.C. for this week, we want to make sure that queries for hotels in D.C. are fast.
Yes, good point. Yep. So essentially, since again, actor model makes it so adaptive and easy because the implicit sender gets passed as a parameter. We really don't have this compile time binding, so we can actually flip this and have a query cache layer built on top of it. You want to talk about the same?
Yeah, so what the query cache does is, given a query, if I've already run the query recently, say for DC hotels, I already had a response list out of the search tree, so I don't need to hit it again. I can just return immediately the results because I already know them. We'll assume that they don't change. This doesn't have any sort of cache invalidation, which you would have to add in real life, but we'll cover that. That's an advanced topic. Anyway, so here's what the query cache looks like. I have a LRU cache. This is really, really lazy. It's a Java linked hash map or whatever, and has evict oldest entries. And it just has the query string and then the hotel response that the search tree gave us. That's what's in cached queries. And there's a number of them that's configurable in the actor, in the constructor. This cache queries int is how many we want to cache. Okay, so given a response of a hotel query, somebody has called us with a query. We check to see if it's in the cache. We get the value in that query string. We wrap it in what's called a Scala option. If we got nothing out, okay, then we know that we have to send the query down to the actual search tree, which I'll cover later. If we have it cached, we just respond with the cache immediately. So if you remember in the fail whale example that I showed, I accidentally searched for the query A, which was already in the cache. This is in front of our failure detector, so this thing can respond to the most popular queries all the time. We only have 3 of them with results, even if the backend service is down, which is pretty cool. Anyway, so if I don't have the query, what I do is I create an interceptor. This is the same pattern. Okay, I need to keep track of the actual session for a message that came in, like what's happening with that message as it flows. So I create someone to take the response and know who it came from and what it's about. So I create a query interceptor that remembers the query string, remembers who was supposed to listen to it, and he also has a reference to me, the cache. Okay? What he's going to do is when he gets a response, if it's a good response, he's going to tell me, update your cache, this query has this response. I'm going to put it in the cache. Since it's an LRU cache, if I get a bunch of different responses, eventually stuff will fall out. Okay, so this only has so many in memory. Does that portion of code make sense? Okay. Here's the interceptor. The interceptor's simple, right? When I get a hotel response, I tell the person who wanted it originally, and I send the update cache query based on the query that I knew about. This is the state I'm maintaining, and I send it to the cache, and then I kill myself. So these little session actors, I call them, are pretty much, I detect what's happening with the session of a message and then tell people who need to know and kill myself. It's the kamikaze interceptor. Okay. Yeah, so any questions on this query cache? Now what's interesting with the query cache is the query cache runs, I can run that on a set of threads, which is completely different than the search hierarchy. Okay, I can actually control which set of threads they run on, and now I have completely decoupled components. So I can have my failure detector and my query cache on different threads, so that this guy might have more, the failure detector might have 1 or 2, and then the search tree might have however much we think he needs. And I've isolated the thread contention. So the query cache gets the really high, availability threads, and he is responding to things really, really fast. And when I have to hit the search tree, I have a bunch of threads available to scale out and start using all my CPUs. But if that set of threads starts to die, the whole system still responds because he's on a separate core of threads. Yes? Yes.
Right.
Yeah, so the question is, some of the actors are long-lived, and they handle tons of requests. Yes.
But some of them just exist for a second.
And some of them are yes, some of them only exist for a few seconds or whatever.
They just represent a transaction, basically.
Yeah. So next, we're going to try to go non-blocking all the way.
So where we go from here, then what's the next step? We're necessarily not going to show that in the code because, so what we have done so far is that apart from the request coming into our controller and is going to our service, everything is kind of event-driven and asynchronous. We are not blocking anything. And blocking is a very costly operation to have because you're blocking a thread waiting for something to happen where you could have done something else. You could do some other work. So the piece of code that we worried about in this entire application is it in the Akka search bin? Mm-hmm. Yeah, is this await call right here. The only reason we are doing that await call right there because the protocol, the mechanism that Spring is using right now is completely synchronous request response. Now we want to go completely non-blocking. There are new frameworks coming into the market which actually can allow you to do that. Wouldn't it be nice that we could actually hook into that feature and say, when you are done, please send the message to the browser and free up the current thread that's actually handling your request so that that thread can go back to the pool and handle the next request, right? So there is a tons of opportunities and scalabilities that we could perform beyond that. So I think there's a future coming. I think the Spring 3 is also supporting that async sublet mechanism, right? The async sublet's coming and it's kind of very exciting to do that because that will fit really well with the actor model. So you can take your whole application event-driven altogether. Oops. So these are some of the companies that we have that's actually using Akka. It's not that project that is just brand new. There are actually people relying on it, building application, production quality applications running on them. There are a few of our clients for Typesafe which actually does that. And Akka is essentially placing itself as a concurrent toolkit also. I mean, there are frameworks which is building on top of Akka and using Akka for interesting stuff. Like Play, for an example, Play is a web framework but uses Akka actors as a request response handler mechanism. So doesn't use threads, so it becomes a really, really interesting stuff. That's all we got here. And so any questions? Please, I encourage you to check out the code base because that uses a Maven Spring application. It will allow you to, yes, please.
Where can we find your slides because it wasn't on the thumb drive?
I will make sure that because we prepared it yesterday. So we will make sure that I put the slide on that same URL. Yeah, I'll create a folder there. And
there are talks that involve actors without Spring that you can find, say, on if you search for Akka, like Victor Klang's, and I have one on jsuereth.com. But the actual one that involves Spring is this stuff. We'll send that out.
Yes. So the question is, do I have any recommendation for debugging Akka-based application? So there's a twofold answer. I mean, Josh can jump in. The first is that the Typesafe does have a thing called Typesafe Console. If you go to our booth there, you will see an application which allows you to monitor your application. And that's a developer free for developers. You can basically download and use it for your application. And another is that you could do lots of unit testing on actor-based, because Ian covered that in a previous presentation. There is a testing framework. And you can use printlns to do that.
Yeah. So I would recommend looking at the Typesafe Console, the one that we sell. So Akka is completely open source, free to use for anything. And the Typesafe Console is an instrumentation where you can track messages, actors. We really want. We couldn't show it, unfortunately. We tried. But we didn't have enough time because we're way behind. Anyway, the cool thing about the console is you could actually see the search tree. This Akka search tree, by the categories. You can see all the different hotels. You can inspect the actors, see how many messages they're getting, that sort of thing. It's a really, really, really nice monitoring application if you want something, for free. You could actually monitor, if you saw what we were showing, you can monitor yourself health inside of the application by those statistics tracking services, essentially. Yep. So one thing that's always important too with monitoring solutions, we can do the generic. But there's always a specific part of your app where you know better than somebody else how to tweak a particular system or rewire. One of the nice things of Akka is that you can take that knowledge and rejigger the whole topology, or a portion of it as needed at runtime. So, the whole let it crash mentality kind of applies to some extent here, if that helps. The Typesafe Console is a great way to learn what code to write to do that. Yeah.
Any more questions? Yes, please.
So multiple actors share the same thread. The issue we have here in the Spring world, there's stuff that's on the thread. Like open session review and all this other stuff. Is there actual usage of Akka, like in an actual Spring app? Can we actually use it for anything? Because I can't really have a transaction, right? Because it's it's on a thread. The session is on a thread. If I use Hibernate, everything is on a thread, and this is very loosely using threads, right?
So there is a way to get transaction. The question is, can I use Akka in Spring with the way Spring does transactions because they attach everything to threads? So the answer is that obviously you can't attach to threads for things inside of Akka. So that's where things start to deviate. It's best to treat it as a sort of a remote service that lives with your Spring. So I send it messages and they come back. Akka does have a transactional model where you can kind of tie transactions to actors. The problem with transactions is that you're taking something, a big block of code, and you're making it be sequential. And you're making it so nothing else can happen during that transaction. And so you always end up with bottlenecks with that. So Akka is going to make you think about your design in a slightly different way. So you pass messages along in a flow, and then at the end you determine whether or not it's good, and commit to a database in a very, very small transaction. You would send. It's best to design your system in that fashion, and you get far more scalability across things. But again, it's a completely different mindset of how you think about flow and writing code. Yeah.
Yeah. Yes. So so the question is, what kind of tools do we have to kind of visualize your actor system while it's running? So we have a tool, we kind of a little bit talked about it. We have a tool called Typesafe Console, which kind of plugs in it. We basically have some actor jars which kind of allows you to view that. So it's an application which hooks into your actor system and gives you a visualization of how your actors are performing, how the messages are going, what's the latency of the system and everything. And yeah, so it kind of annotates your messages. So what happens is there is a bytecode weaving happening behind the scene. So when you're using a console, you have to kind of use a separate set of jar files that you can plug in while monitoring. Yeah. But you can set the threshold, you can set the sampling rate as well.
So the question was about injecting messages too. One of the beauties of Scala, which Groovy has as well, is we have a interpreter, a REPL, where you can type Scala code live into a running system and write code. So if you want to inject messages, it's actually as simple as starting everything up inside of the REPL and just shooting messages in. That's how I debug most of my systems. And you can attach the Typesafe console to that REPL session. You can attach a Java debugger to it. It's awesome. So you would actually, the way that I've done that in the past is they have this notion called a worker actor where you pass it that receive function, and then when it gets a receive function as a message, then it would cause context become what it just got. You can do that.
Yep.
One thing that I will say is since the topology of actors is a very dynamic thing, runtime thing, the IDE tools, we don't have static, like let's view the topology statically of what you've defined, the way you would see in, say, Spring integration with the XML. Because it's dynamic, we want you to change it and think about it at runtime. That's why the Typesafe Console, looks at it that way.
Yeah.
Nodes get hit a lot. Is the cache, how often is it given? How hot is that cache? Seeing the topology change. Just, instead of, I saw you guys go into the log a bunch to see stuff. Sort of seeing the change based, and I understand why you're doing that in a simple demo, but for a more complex system, it seems like you get overwhelmed by the amount of content in the log.
Yeah, so we're actually really running out of time.
Yeah.
We're over by 3 minutes. I don't want to hold you guys too far, so we can talk more afterwards. But go to the Typesafe booth. It has a demo of the console. You'll get to see like the richness that we have in terms of visualizing what's going on and everything. Yeah.
Last question, one more question. Anybody? Question, yes. Yeah.
We saw that when you're setting up, like, say, remote actors,
Right.
you have to explicitly lay them out. Is there, with the clustering, the notion of, like, kind of a configuous agent where you could put an agent on another box and have it ping back into, say, the main application, say, hey, I'm up and available, wait.
Yeah, so Akka cluster uses gossip protocol. So they're going to implement that with basically gossip, figuring out which node is up and which node is down and replicate that.
Clustering features.
Yeah.
Yeah. So,
Not there, no.
in 2.1, there's a cluster membership. It's considered experimental because it works, but they don't know if the API is what people want, so they want the ability to change the API. But you'll get notifications when someone joins the cluster, and you'll be able to do things based on cluster membership. In the future, we hope to go way further, like automatically taking portions and moving it if you configure it that way, that sort of thing. So,
All right. Thank you very much for coming. Okay. Thanks.